Welcome to the last chapter we will cover in semester 1 of organic chemistry. The good thing about this chapter is that there's a lot of overlap with things we have already learned in previous chapters. What this means is that there's less new things to learn, but also it serves as a good review as we round out the semester. We will first provide a brief introduction to alcohols and phenols, their nomenclature, and their physical properties. We will then talk about the acidity of alcohol, which should be a review for you. Then how to make alcohols via substitution and addition reactions. Again, review. Finally, we will jump into a new class of reactions by looking at how to make alcohols by way of reduction. So as we mentioned before, in this chapter, we are taking a look at alcohols and phenols, and we will be breaking this down into 2 lectures. So in this lecture, we will be introducing what are alcohols and some of their properties and how they are produced. So if we break it down, fundamentally, alcohols are any molecules that possess this OH group. The OH group is also known as a hydroxyl group. So example we have here is ethanol and cyclopentanol. And in fact, this functional group is quite pervasive in nature, in natural compounds. One prominent example is cholesterol, which is important in the biosynthesis of vitamin D and hormones. Another common example is glycerol, which you often can see in your lotion. Alcohols and phenols are quite similar, except in phenol, the hydroxyl group is directly attached to a benzene ring. Some examples of phenols is this bisphenol A or BPA, which is used in making some plastics. You can also see phenols in a lot of aromatic compounds. And when I say aromatic here, I mean compounds that smell good in cooking. For example, curcumin is a main compound in turmeric. It has that phenol group. Or this molecule that is responsible for the smoky smell of barbecue. All right, so let's talk about how to name compounds with the alcohol group. So their naming is basically the same as if you had an alkane, except for these 3 important changes. First, you have to identify the parent chain, which now must include the carbon chain that has the hydroxyl group. Second is that you have to give the carbon that the hydroxyl group is attached to the lowest locant number possible. And the third difference is when you name it, the hydroxyl locant is placed either just before the parent name or just before the OL suffix. All right, so let's see each of these rules in action. So in our first example here, we have pentane, which is a 5-carbon chain. At the end of that chain, if you add a hydroxyl group, it just becomes pentanol. So you drop that E and add that OL. So let's see how we can apply this first rule here. Notice that in the alkane, the longest chain you can draw is 8 carbons, where you have a methyl substituent. Now, if you add a hydroxyl group to that methyl substituent at the end, your parent chain will be a 6-carbon chain, even though you can have an 8-carbon chain that's longer, right? Because the parent chain must include the hydroxyl group. So no longer is this the parent chain with 8 atoms, but it is now this as a parent chain with 6 atoms. So the parent name is hexanol, and this becomes a substituent. Because we are paying a special attention to the hydroxyl group, when we number our chain, we also must give it the lowest locant possible. Meaning in the parent chain, you have to start at the end that sees the OH first. For example, in this molecule, if you start numbering it from the left, OH is seen as number 2. If you start counting from the right-hand side, the hydroxyl group is seen at carbon number 6. So 2 is lower than 6, so the correct numbering of this parent chain is on the left. And yes, we do see that the alcohol group has higher priority in nomenclature than the alkene. So here's a quick list of functional groups and their priority. The higher ranked it is, the higher priority it has. So groups from 1 through 8, you may have not seen yet, but we have seen alkenes and alkynes. And notice they are at the 12th position. So they are very low in priority as compared to alcohol. So that's why we give preference to alcohol in naming and also in the locant. And you will use this list as we get to more and more complicated molecules with more functional groups as we proceed to subsequent chapters. And lastly, how do we name it with the locant of the hydroxyl group? If it's a simple molecule, we can place it at the beginning of the name. For example, 3-pentanol, the locant 3 can be placed in front or just before the OL. So it could also be named as pentan 3-ol. All right, so let's go back and name this compound. As we said before, we number it starting from the left-hand side so that the alcohol receives the lowest locant possible, which is 2 in this case. What are the substituents? You have 3 substituents. They are all methyls. So we will identify all of those methyls individually. So 5, 5, 6, and there's 3 of them, so we say trimethyl. All right, so at this stage, we can name the parent chain, which is the 7, so heptane. But it's not a simple alkane, since there's a double bond, so we have to indicate that the double bond starts at carbon number 6. So we put a dash in 6-ene, and finally, the parent functional group is the alcohol, and it's at number 2. So this gives us our complete name. 5, 5, 6, trimethyl hept 6-ene 2-ol. Again, the 6-ene is where the alkene starts, and the 2-ol is where the alcohol is located at. For cyclic compounds, the hydroxyl group is always carbon number 1, so you don't have to specify an actual locant for it. So for example, here we have cyclopentanol to the left, and to the right, simply call it R, 3,3-dimethyl cyclopentanol. And there are some alcohol molecules with common names that you should be familiar with. Like for example, 2-propanol is also called isopropyl alcohol or isopropanol. 2-methyl-2-propanol could also be called tert-butyl alcohol or tert-butanol. And then phenylmethanol, where you have a benzene with one carbon and then a hydroxyl group, is sometimes called benzyl alcohol. Like halides, alcohols are often classified by the type of carbon they are attached to. So at the alpha carbon is described as the carbon that is attached directly to the oxygen. So if the alpha carbon has only one R group, we can call that primary alcohol. If that alpha carbon has 2 R groups, we call that secondary. And if it has 3 R groups, we call that tertiary alcohol. When the hydroxyl group is attached to a benzene ring, the parent name is phenol or phenol. So we have here a phenol with a chloro and a nitro group. And so this is called 4-chloro-2-nitrophenol. And actually we'll leave it at that for now, as we will dive into more of this nomenclature of the phenol when we go to the aromatic chapter later on. So now let's talk about some alcohol molecules that are important in industry and therefore in society. And these molecules are produced by the billions of gallons every year in the United States alone. The first is a 1-carbon alcohol, the methanol. Methanol is quite poisonous and very toxic. However, it has a lot of uses. For example, it could be a solvent in a reaction or a precursor in a synthesis, and it also can be used as a fuel. A second molecule here is ethanol. Ethanol is basically methanol with 1 methyl group attached to it, so an extra carbon. And as you probably know, it can be made by the fermentation process of sugars from grains and fruits, right? That's how you make beer, that's how you make wine. But industrially, ethanol is made by reactions we've learned in previous chapters, which is the acid-catalyzed hydration of an alkene, more specifically, of the 2-carbon alkene, the ethylene. It has the same uses in industry as methanol, but what makes ethanol stands out is that it also can be consumed. As we have seen before, it is the primary ingredient when you drink. And lastly, isopropanol, which is a 3-carbon chain with an alcohol group attached to the middle carbon. You may know this more as rubbing alcohol. Again, just like methanol, it is poisonous, but it's very useful as a solvent and antiseptic. Now let's talk about some physical properties of alcohols. Specifically, we'll be highlighting boiling point and this idea that might be new to you called miscibility. Let's first start with boiling point by looking at these 3 molecules: ethane, chloroethane, and ethanol. Ethane has a very low boiling point. of negative 89 degrees Celsius, whereas chloroethane has a more elevated boiling point of 12 degrees Celsius. And then ethanol has the highest boiling point among these three with 78 degrees Celsius. So recall why that is. Remember what dictates boiling points, right? Boiling points are dictated by the attractions of the individual molecules to each other, right? So what dictates their attraction? Intermolecular forces. Very good. So ethane has really only one intermolecular force. Remember that was the London dispersion force, right? So that's not very strong in ethane because it's a nonpolar molecule. Then when you move to chloroethane, you now have a electron withdrawing group. So now you have a polar molecule. If you have a polar molecule, you not only have London dispersion forces, but you also have dipole-dipole interactions, so causing more attraction, so higher boiling points. Now, with the OH group, it is also an electron withdrawing group, so it also has a dipole-dipole, but why is it so much more than the chloroethane? Right? So remember that it also has what is known as hydrogen bonding. Okay, so because of this hydrogen bonding, molecules with this alcohol group tend to have higher boiling points. Now let's talk about how alcohols can mix with water. When things are mixing well with water, the term used is called miscible. So it turns out alcohols with 3 carbons or less are miscible with water. Remember, if it has just carbons on it, it is basically a non-polar side. Whereas the hydroxyl group, that's the side that it's polar. So the more non-polar side molecule has, the less it can interact with the polar water, right? So if that carbon chain is elongated, so in this case, 1, 2, 3, 4, 5, 6, 7, 8. So in this case, you have 8 carbon chains here. That non-polar region outweighs the polar hydroxyl region, so making this molecule essentially more non-polar than is polar. Because of that, it doesn't mix well with the polar water molecule. Okay, and so because of that, we call that non-polar region the hydrophobic region, whereas we could call the other end where there is a hydroxyl group the hydrophilic region. Hydrophilic means loving water, right? So it likes to mix well with water, whereas hydrophobic, hating water, because it is non-polar, it doesn't mix well with polar water. Now let's pivot back into the reactivity of alcohols. First, we will explore the acid-base reactions of alcohols and phenols. Like I mentioned, this part should be a review for you from the acid-base chapter. We will start with taking a look at what is strong enough to deprotonate an alcohol. The most common reagent here is using a hydride. For example, sodium hydride, it can be used to deprotonate the proton in the hydroxyl group. And the product of that is what we call an alkoxide. So an alkoxide is basically the alcohol that has been deprotonated. So in this case, the ethanol becomes an ethoxide. And as a byproduct of that, hydrogen gas is evolved. Another way to create that alkoxide is throwing ethanol into pure metal like sodium, potassium, or lithium. And in the same way, the product of that is an alkoxide, and the byproduct is the hydrogen gas that evaporates. So let's focus on these alkoxides and see their strengths. And so if we were to compare it across the table here, we have on the left-hand side, the least stable because of the carbon is not very good at accepting the negative charge. As we move more towards the right-hand side of the periodic table, it gets more electronegative from nitrogen to oxygen to halogens, right? As we move towards the halogens, it is more electronegative, so therefore it is better at accepting the negative charge, better at stabilizing the negative charge. So because of that, these negative ions are more stable as you go from left to the right on the periodic table. Now remember in chemistry, when something is stable, it doesn't want to react, right? So you can say that the X minus is the least reactive, whereas the R minus is the most reactive as a base. Now let's review how that affects the acidity of the conjugate molecules. Again, if you have halogen, the X minus there, if it is the most stable, then its conjugate acid, X
H, or for example, hydrochloric, hydrobromic acid, that is going to be the most acidic. It wants to react the most, right? If X minus wants to react the least, then XH wants to react the most. And so if we can recall, that's why alcohol is not that strong of an acid. It is going to be weaker than your hydrochloric acid, for example, but it is stronger than your amine. And you see there the pKa of an alcohol is between 15 to 18, whereas an amine is between 35 and 40. And one key difference between an alcohol and a phenol is in their acidity. Okay, notice that these two molecules have a similar structure, except the phenol has a benzene ring, and with that aromatic ring, it increases the acidity of the hydroxyl group. Okay, so cyclohexanol here, for comparison, has a pK of 18, whereas phenol has a pK of 10, so millions of times more acidic than a regular alcohol. So why is that? Why do you think a phenol is going to be so much more acidic than its analogous alcohol? So remember back to ARIO, A-R-I-O. Which feature of ARIO will explain why phenol has a stronger acidity? Is it the A, the atoms? No, right? Because both of those hydrogens are attached to oxygen, so they have the same atoms. So what's next in ARIO? R. What does R stand for? Resonance. All right, does one of these molecules have resonance? Yes, right? The phenol has resonance. So let's take a look at resonance. Once you take away that hydrogen, the negative charge on the oxygen can be spread throughout the benzene ring via resonance. As you can see here, it has multiple resonance structures. And so that negative charge is being spread around the atoms of the benzene ring, spreading the love, spreading a negative charge, making it more stable. And because it is more stable, the conjugate acid is going to be more acidic. All right, so that's one special feature about the phenol. It has a much more acidic hydrogen.
So now let's talk about how to make alcohols. As promised, this part will have many overlaps with previous chapters, so it should be a review for you.
We've learned ways to make alcohols in the previous chapters. For example, using substitution reactions. If we have a primary alkyl substrate, then you probably want to go with an SN2 reaction because that alpha carbon is available for nucleophilic attack. So a strong nucleophile you could use is sodium hydroxide in this example here. Now, if you have a tertiary alkyl halide, you cannot do SN2 because the alpha carbon is too sterically hindered. So instead, you can go about using the SN1 pathway. All right, so again, we've seen this already, so this is a good time to review the substitution reactions if it is not fresh in your mind. Another way to prepare alcohols that we also have seen before is when we have an alkene, we can hydrate it. Okay, we can do this in many ways. Remember, hydration means adding a hydrogen and an OH across the double bond and essentially creating an alcohol. Okay, the first way we've seen this is using acid catalyzed hydration. And remember, this would be a Markovnikov hydration, meaning that OH will be added to the more substituted carbon, and hydrogen will be added to the carbon that has more hydrogen already. And as you may remember, acid catalyzed hydration is great, but it goes through a carbocation intermediate, and because of that carbocation intermediate, it could have rearrangement and giving you different products. So if you want the Markovnikov hydration, but without any rearrangement, you would try the second method here, which is oxymercuration in the first step, followed by demercuration in the second step. Now, if you want the anti-Markovnikov product, what would you do? The last reaction here, the hydroboration oxidation, again, a two-step reaction that will give you the anti-Markovnikov product, where the hydroxyl group will be added on the less substituted carbon. Again, all of these should be reviewed for you from the alkene chapter.
So the third way to prepare alcohols will be new to us, so the bulk of this video will focus on this new method. This method is by way of reductions of a class of molecules known as the carbonyls.
So remember, what is the carbonyl? It is a carbon doubly bonded to an oxygen, right? And so let's backtrack a little bit. I mentioned that is a reduction. So what does a reduction mean? A reduction involves a change in oxidation state. All right, so that could be a new term for us. What is oxidation state? Well, oxidation state is basically a method of electron bookkeeping. Electron bookkeeping. That sounds familiar? Remember, we've seen that already in terms of formal charge, right? Where each atom is assigned half of the electrons it is sharing with another atom. So let's see an example of that using methanol. So let's focus on the left-hand side here. If you have methanol in a formal charge, we say that each bond has 2 electrons, and each of those electrons are being shared equally among the 2, right? That carbon and the hydrogen each has its own electron. That carbon and that oxygen each gets its own electron. That's called homolytically cleaving the bond. So when we do that, we notice that carbon then has 4 electrons, and since it is on the 4th column, 4 minus 4, its formal charge there is 0. Now on the flip side of this, when we talk about oxidation state, we don't break the bond evenly. We know that atoms that are more electronegative will be more hungry for the electrons. So when we break this bond, again, we're not actually breaking any bonds. This is just a way of bookkeeping, right? So let's focus again on the carbon and the oxygen bond there. Once it breaks that bond, both of those electrons go towards the oxygen because the oxygen is more electronegative than the carbon. Whereas the bond between the hydrogen and the carbon, when those bonds break, both of those electrons go towards the carbon, none towards the hydrogen. So now let's count how many electrons are on carbon. 6 electrons, right? So 4 minus 6, so the oxidation state is -2. All right, let's do another example of oxidation state. Here we have an aldehyde. Let's first take a look at the relationship between the carbon and the oxygen. Remember that the oxygen is more electronegative. So both of those bonds, or 4 electrons, belong to oxygen. Now let's take a look at the carbon and the hydrogen. Carbon is more electronegative than the hydrogen, so that bond, the 2 electrons belong to carbon, giving hydrogen nothing. And lastly, the bond between carbon and carbon, well, they are equal in electronegativity. So in this case, they will share it equally. So 1 electron goes to each. All right, so the central carbon here is left with 3 electrons. So the oxidation state is 4 minus 3 is +1. So we say that its oxidation state is +1. So the oxidation states for carbon can range from -4 to +4, as we've seen here from methane to carbon dioxide. Well, notice as you go from left to right, you are adding more oxygens. The more oxygen the carbon is bonded to, the more electron is being withdrawn towards the oxygen, so making the carbon more positive. So let's notice here, from methane to methanol, you're attached to 1 oxygen. Your oxidation state went from -4 to -2. Now, from methanol to formaldehyde, you don't actually see 2 oxygens, but we see that the carbon is now bonded to the oxygens twice. So essentially, that's the same as being bonded to 2 oxygens. So because of that, its oxidation state is now 0. It's being more positive. As we move to formic acid, you add another oxygen, and as you move to carbon dioxide, you add another bond to oxygen. Notice as you're adding more oxygens, you are being more positive, and so we call that being oxidized. So that's the original why it's called oxidation, but in fact, anytime that carbon is being bonded to something that is more electron withdrawing than it is also considered an oxidation reaction. So again, the oxidation reaction is more broadly defined as when carbon's oxidation state is increased. So the opposite happens when you have a reduction reaction, when the carbon's oxidation state decreases. So let's say from formaldehyde to methanol, it goes from 0 to -2. Then we have what is known as a reduction reaction.
All right, with that, let's bring our attention back to the method of synthesizing alcohols by way of reduction.
So as we said before, when we turn a carbonyl to an alcohol, it requires a reduction pathway. And as we said previously, an oxidation is basically adding oxygens to a carbon, while reduction is the opposite. Reduction is basically when you're adding hydrogen to that carbon. So there are three ways of doing this. The first we've seen already is called catalytic hydrogenation. When you add hydrogen gas over platinum, palladium, or nickel catalyst, you can add hydrogens across that pi bond, one to oxygen, one to the carbon of the carbonyl. Now this theoretically works, but in practice not as useful as it requires high temperature and pressure. A more common way is by reacting it with hydride. The second method is using sodium borohydride. Sodium borohydride, again breaking out that name, sodium is that cation, boro is representing the boron, and hydride is the negative hydrogens. And sodium borohydride is used to reduce mainly aldehydes and ketones. In this reaction, you may have a solvent like ethanol, methanol, or water. All right, let's draw the mechanism of this reaction. And so we have the carbonyl and your sodium borohydride. Remember that sodium borohydride is your source of hydride. And notice that the negative charge is drawn on the boron, but that's not where the electron density is. You can redraw this compound to indicate that the hydrogen is more electronegative than the boron, and so clearly show why this is called a hydride, because now the hydrogen has both of those electrons, so therefore has a formal charge of -1. A hydrogen with a negative charge of 1 is called a hydride. So that's where the source of your nucleophile will be. So you can draw it attacking your carbonyl. But I'm going to show you how the book draws it, and it's the same way, so either way is acceptable. So the nucleophilic attack happens from that BH bond. With that nucleophilic attack, it also breaks the carbon-oxygen carbonyl double bond. All right? And so now we have created this alkoxide with a negative charge on the oxygen. At this point, you may have a protic solvent like water here that will provide the source of proton. Upon the proton transfer, as the last step here, we get our alcohol. Okay, notice that when you have an unsymmetrical ketone, which basically means it has two different R groups, like in this example here, we have the ethyl group here and a methyl group on either side of the ketone. When you have that unsymmetrical ketone, you will get a racemic product. What does that mean? You will get both enantiomers of the alcohol. Recall why that is. Remember that the carbonyl is trigonoplanar. Because it is trigonoplanar, the nucleophile, the hydride, can attack the carbon from both sides, from the left side or from the right side, giving the R or the S enantiomer as products. All right, so just keep that in mind when we talk about reduction of unsymmetrical ketones. And lastly, the third method is using lithium aluminum hydride, also abbreviated as LAH. And so again, we have LAH as our hydride source to go in and do an attack. Now, the only key difference is that LAH is very strong, so it cannot be combined with any source of protons. So you must add water as a second step and not together in the first step. Just to compare with sodium borohydride, LAH is super similar. Instead of the boron, we have the aluminum as our coordinating metal. And because aluminum is less electronegative, the hydride is even stronger, even more electronegative, fully charged with electrons than in sodium borohydride, making LAH much more reactive, which is one of the reasons why we don't add it with water. All right, so let's review here. If you have a ketone with an alkene, if you use the first method we talk about, both of those pi bonds will be reduced. The ketone and the alkene will be reduced if you use catalytic hydrogenation, right? But if you use the hydride methods, it is more targeted on the carbonyl and will leave the alkene alone. The reactivity of the hydride delivery agents, the H-, can be fine-tuned by using derivatives with varying R groups. So you may see aluminum or boron in the middle, but instead of hydrogens on the outside, it could be different R groups. And these R groups can be alkoxides, cyano groups, or you can even design it to be sterically hindered R groups. All right, so the difference here between LAH and sodium borohydride, not only do you have to add water at a different step in the reaction, But in the fact that LH is so strong, it can also reduce esters and carboxylic acids. Sodium borohydride cannot. All right. So for example, here we see a carboxylic acid. If you use 2 equivalents of LAH followed by water, you will create a primary alcohol. Or if you have an ester, you use 2 equivalents of LAH followed by workup with water, you will have a primary alcohol also. Okay, so let's see what the mechanism looks like for the reduction of this ester. And we also have our reducing source here, the lithium aluminum hydride. Again, you see the negative is on the aluminum, but really it's actually on the hydrogen. It's actually the hydride that's doing the nucleophilic attack. Just like in sodium borohydride example we saw previously, it does a nucleophilic attack, breaking the carbonyl double bond. And remember, in this reaction, there is no protic solvent around, so that alkoxide won't just pronate and become an alcohol at this step. Instead, though, what happens is that that lone pair collapses back down, reforming the carbonyl. And because of that, that carbon of the carbonyl cannot accommodate too many electrons, so something has to give. R and H cannot leave because it's very unstable as a leaving group. This OMe module, however, is able to leave. Now, we've learned from a previous chapter that OMe is not a very good leaving group, right? So why does it leave in this case? Well, there's one key driving force here. This intermediate is highly unstable compared to the aldehyde product that is formed. The double bond between the carbon and the oxygen, the carbonyl double bond, intermediate is highly stable, so it sacrifices the OMe being a bad leaving group to achieve this stable aldehyde intermediate. Now with this carbonyl reestablished, remember that the carbon of the carbonyl is very electrophilic, right? So because it is electrophilic and there's more hydride around, it is primed to be attacked once again by the hydride source, which is why in this reaction you need an excess amount of LAH. You need 2 equivalents to be exact, because the LAH attacks in the first case of the ester and then it attacks again in this case with the aldehyde intermediate. This time I'm going to abbreviate it as so. Okay, the nucleophilic attack, very similar as we've seen before with breaking of the carbonyl bond, right? So that's the second equivalent of the hydride being added. There's 2 hydrogens attached to that carbon now. All right, and in a separate step, in the final step, we add in the water for the proton transfer step. And so finally, we have our primary alcohol as our final product. All right, now let's quickly introduce you diols, from the name diols meaning 2 alcohols. Now the naming of diols are very similar, except you just don't drop the E of the parent chain. For example, here this is a 3 carbon with 2 alcohols on each end. So the first alcohol is on carbon 1, the second alcohol is on carbon number 3 there. So we call this 1,3-propane diol. See that E is not dropped. Second example here, it has 5 carbons, 1 hydroxyl group on carbon 1, second hydroxyl group on carbon 5, so we just call it 1, 5 hexane diol. A more common term for diols you can also come across is glycol. For example, here this is ethylene glycol. And so how can you make diols? Well, you can just make diols from the reduction of 2 ketones, right? So the 3 methods we learned just now. If you want to make 1,2 diols, you can also make them from the methods we learned from the alkene chapter. Remember we learned that in the first method here, we can make an epoxidation reaction with an alkene followed by ring opening to give us the anti-dihydroxylation. Alternatively, we can use osmium tetroxide, OSO4, with a co-oxidant NMO to give us a syn dihydroxylation product. Right? We can also do that with CaMnO4, for example, cold potassium permanganate. All right, so review that from the alkene chapter if that's not fresh in your memory. All right, so we'll stop here for now, and we will come back with a second part looking at newer reactions.